Hello. We'll get started with the 1:8 synthesis problems, and I think Maggie, you're from 8B, right? Yeah. So we'll do 8B afterwards. I recently just created this chart of the carboxylic acid derivative reactions, right? This is going to be the azo halide. This is going to be the carboxylic acid. This is the ester. This is the amide. And all of these rows here are going to be the reagents that you can see. And here are like the reactions that you need to know and the names of the reactions as well. Most of them are nucleophilic azo substitution mechanism. And like there's some extra notes as well, and I could go over how to use this chart, how to read this chart as well, and this will definitely help you identify what reaction you're gonna do, right? So before we get started with that though, let's do the 118A synthesis films that I created some last night, I think. Yeah. When was that? That is going to be March 11th, this one. Yes. Okay. So let's copy this page. Okay, so for this synthesis problem over here, what I like to do is I like to think about it retrosynthetically, so going backwards, right? So the first thing I do is I find my similarities, and I'm gonna highlight the similarities in yellow here. This part of the molecule right there is this part of the molecule right there. And I see that the differences are these groups right here, right? The OH group is no longer there, the BR group is new, and this R group is new, right? So thinking of that now, I am going to start thinking about what reactions can give me this new R group. So in monocyte A, this is one of the newer reactions that you're learning this quarter. What reaction do you know that adds a new R group to the molecule? Grignard reagent, yes, correct. So we know that there's going to be a Grignard reagent somewhere in the mechanism. Right. If we see that this carbon here is the carbon right there that remains the same, and this is the new R group right here, right? We could say that this dot carbon that I just dotted out was the electrophile, right? So that was attacked by this Grignard reagent here, and our Grignard reagent was this MgBr right here, right? Where that starred molecule here is our nucleophile that attacked this dot carbon right there. Now, do you know what Grignard reagents usually attack, Kelly? Like what kind of reactants they usually use to attack with? Right? Like if we were given this Grignard reagent here, there's actually like a few things they could react with. They could react with a primary haloalkane. It could react with a ketone or aldehyde with acid workup, or it could react with an epoxide. I think those are the ones that you've learned for now, right? So we're gonna use one of these reactants here to create this structure, right? Let's say that this was turns into a carbonyl, right? Like this blue carbon here was a carbonyl carbon because a Grignard reagent here can attack a carbonyl carbon right there, right? Giving an OH. So what reaction do you know that converts this OH into an alcohol? This is one of the newer reactions as well, like one of the newer reactions, that alcohol reactions that can convert this secondary alcohol into a ketone. There's two reagents you could use here that you learned so far. PCC, yes. PCC or Jones would work. That would convert that secondary alcohol into this ketone right here, right? That would make this carbon here now electrophilic because it's positively charged. Then we can bring in our Grignard reagent that we figured out from the star, right? That's the RMGBr, where this starred carbon here is the negative charge carbon, the nucleophilic carbon, right? When this star carbon attacks that carbon right there, we have to push the double bond onto the oxygen because we're making a new bond between the star and dot carbon, right? That breaks the octet rule. So that means that we have to push this double bond onto oxygen to conserve the octet rule, giving that oxygen a negative charge. And that negative charge is going to get protonated by acid workup, H3O plus, to give us this OH here and this R group right here, where this is the dot carbon, this is the star carbon, this is the new bond between the star and dot carbon. Does that make sense so far on like how I'm getting these reactions in the synthesis and my thought process behind this? Any questions on why I thought of these reactions in the way that I did, in the direction I did? Yeah, let me draw out the second step mechanism clearly, so it is more clear to you. Let's say we have this ketone right here, right? And let's say we have this Grignard reagent right here, where this is the R group and this is the MGBr. So when you see MGBr, right, the carbon directly attached to the magnesium, the Mg right there, is negatively charged, partial negatively charged, right? So that's my nucleophile right there. The carbon directly attached to the Mg. This carbonyl carbon right here has a partial positive charge because it's attached to this electronegative atom oxygen right there. This electronegative atom oxygen is withdrawing electrons from the carbon, right? This carbon here is losing electrons, becoming positively charged. And that is the electrophile for this reaction. This is the nucleophile, this is the electrophile. In OChem, the nucleophile will attack the electrophile like that, right? So we're making a new bond here. We're going to make a new bond between the star and dot carbon. The MGBr here dissolves away in the solution. Like it just disappears into ions, right? When we make a new bond between the star and dot carbon, the dot carbon will have way too many bonds. It's going to have 1, 2, 3, 4, 5 bonds. That's not good. We don't want that. To conserve the octet rule, we're going to pop this double bond into the oxygen like that to make sure that this carbon keeps its 4 bonds, right? But this oxygen here has 2 pairs of electrons. One bond of the double bond here, those 2 electrons are going to go onto the oxygen as a pair of electrons, giving that oxygen 3 pairs of electrons and a single bond, right? So when I draw out the intermediate, it's going to look like this, right? If I highlight one of the double bonds in yellow like that, that bond right there, its 2 electrons are this right here, right? That's the extra pair of electrons I had, giving that oxygen a negative charge. This is the dot carbon right here. I'm gonna make a new bond between the dot carbon and the starred carbon. Right, this is the new bond right here. This new bond came from this arrow here when the star attacked the dot, right? That attack made that new bond between the star and dot. Now from this point, we draw whatever is attached to the star. The star is attached to 2 methyl groups, 1, 2. So I'm just gonna attach those decorations onto the star, 1, 2. MGBr dissolves away into ions like that. So this is the intermediate we get after that attack. Does that make sense so far? On how I connected those 2 pieces together? Yes, that's good. Now, once we have that O minus right here, I bring in the H3O plus, which is gonna protonate the O minus. So this H3O plus here looks like this. The O minus here is gonna grab one of the hydrogens. The bond between the hydrogen being grabbed and oxygen right there goes onto the oxygen, creating us this neutral OH right there. And then you could draw out the side product if you want water. But that gives us our neutral OH. It turns O minus into neutral OH when you put acid workup. It could be H3O plus, it could be HCl, or it could be H2SO4. Any strong acid, any proton source, anything that could give a proton, a hydrogen on the oxygen to make it neutral. Any questions on that part of the mechanism? No, okay, that's good. So that's the second part right there. And once we get to this point right here, we see that the OH here is not there in the final product. Do you know the reagent that converts an OH into Br? This is weird. Like this is like a weird letter, like a weird atom here. It's okay. You don't know. It's gonna be. I'll give you a hint, right? So PBr3, PBr3. Yes, 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 yes. PBr3. Right. If this was chlorine, do you know what kind of reagent you would use if it was chlorine instead of bromine? There's another set of weird reagents with like weird atom. Wait, this is phosphorus right here, but if you want to use like if you want to create Cl instead of Br. SOCO2, does that sound familiar? SOCO2? No? Okay, so she probably did not go over this, so don't worry about that. I will check her lecture notes just in case. Yeah, right. But if you wanted to convert this OH into Cl, you use SOCO2. But because we have Br, we're gonna use PBr3. Okay, so that's that for the synthesis problem. First step, oxidation of secondary alcohol to ketone. Second step, drinking reagent with the ketone to create this new R group with the alcohol. Third step, convert the alcohol to the bromine using PBr3. Okay. Now for this next synthesis problem over here, let's do the same strategy. Highlight my similarities between the reactant molecule and the product molecule, which is this yellow highlighted portion right there. And then I know that the differences is that before we had a carbonyl on that carbon, the carbonyl is no longer there, right? And we have an alkene right here. The alkene was not there before. What reaction do you know that creates alkene so far, Kelly? Like, what reactions have you learned that creates alkene so far in 118A? Elimination reaction. So it could be E1 or E2 reaction. E1, E2. Right, elimination reaction creates alkene. Wait, I'm trying to figure out what I did here. Why did I put two steps here? What's going on? So let's say we have. Oh, I see what I'm doing. Okay. So yeah, elimination, E2 reaction. But what kind of alkene do you see here? Right? What is like, do you think that like at this carbon here, is this the less sub alkene or the more sub alkene? Right? Let's say our other option from this carbon here, our alkene could have been here. Right? Which one is like what is this one? Is this the less or more sub alkene? The one in the product compared to this one? Less sub alkene, yes, right? Because there's one R group only. Whereas this one here that I drew out with you had 3 R groups, right? Now, there is a type of strong base that you could use to create a less sub alkene, right? And that's a bulky base. And there's 2 bulky bases that you need to know. There's turbotoxide, which is this, right? Or you could see it in this form. You can see Na or K with its solvent. Or you can see LDA, right, which looks like that. Right, but you probably won't get this. You probably just get something like LDA or turbotoxide. Those bulky bases will create the less sub alkene. So let's go backwards here. Let's say there was a good leaving group right there, like bromine, right? And if we want to create the less sub alkene right here instead of the more sub alkene, let's use a bulky base like LDA. It's easier to write out, so I'm just gonna draw LDA. You can use turbotoxide as well by drawing it out or drawing out the condensed formula, right? That bulky base would create this less sub alkene right here, the Hoffman alkene, Hoffman E2, right? Now, we see that we want to create a bromine right here where the carbonyl was. Let's go backwards even more. Where do you think this bromine came from? This is gonna use one of the reactions we used in the last synthesis problem. PBr3, yes. So that's gonna be in this arrow, PBr3, and that's gonna come from what functional group? What did this carbon have? before. OH, alcohol. Yes. Okay. Now, how can we convert this carbonyl into OH here? Right. This is going to be the opposite of what we did in the first step in the last synthesis. Yes, it's the opposite. Right. This is oxidation. The opposite of oxidation is reduction. Yes. And what kind of reducing agents do you know that can reduce this ketone into alcohol? What reducing agents do you remember seeing? H3O is an acid, right? H3O plus is an acid. So that's not a reducing agent. Think of that as an acid. NaH is not a reducing agent. Well, it kind of is because it's an H minus, but that's not a common one that we see. Because this is a very strong base. There's a more common one. NaOH. OH minus is a strong base. Right. It's one of those weird ones with, let's say, lithium and aluminum. Lithium aluminum hydride. LiAlH4 or sodium borohydride. Right. So it could be you could use LiAlH4 or NaBH4. Have you seen these before, Kelly? These reagents? Yes. These are your reducing agents. Right? Those would reduce the ketone into the alcohol. And a second step, acid workup. H3O plus. Like that. Okay. So that's that for the synthesis. The first step was reduction. We reduced this ketone into the alcohol. The second step, we converted the alcohol into the bromine with PBr3. The third step, we converted the bromine into the less subalkene using E2 with a strong base, bulky strong base, LDA. Right. Okay. So that is like sort of what my thought process is behind these synthesis columns, the strategies I use, right? I highlight the similarities and differences between the reactant molecule and product molecule. I then start thinking about what reactions can create those differences. And I know that those reactions are going to be in the synthesis somewhere. And then I work backwards, retrosynthesis, and then forward when I get stuck, and then try to meet in the middle after end, right? But you definitely need to know your reactions for these synthesis columns, like what they do. Like reduction reactions, oxidation reactions, organometallic reactions, like Grignard reactions, organolithium reactions, SN2, SN1, E1, E2 reactions, and the two types of E2, like Hoffman E2 or Zaitsev E2. So synthesis is like a boss battle of the reactions. Like you gotta know, it's like a puzzle of reactions. You gotta know the reactions first, and then you could do the synthesis. Okay. Any questions on that, Kelly? No. Okay, that's good. So we're gonna do 8B new material this week, right? This is the carboxylic acid derivative, so chart, which you guys can use if you guys want for the quiz, but we won't go over like the reactions here because I want to focus on the new material, which is gonna be claisen condensation, decarboxylation, and malonic ester or acetoacetate synthesis. Okay, and after that we'll do 118B stuff. Okay. Let's do claisen condensation. So claisen condensation is gonna be like very similar to aldol condensation from the last quiz. Quiz 4, I believe, like the aldol condensation, aldol dehydration, right? I'm gonna give you guys the general reaction and then show you guys the mechanism afterwards. So the claisen condensation is gonna have an ester reacting with an alkoxide ion, right? So I'm just gonna draw out the ester like this, R OR prime carbonyl, but the alkoxide ion here, right, the RO minus, has to be the same exact thing as the OR of the ester, like that. Second step here is acid workup, and we're gonna go over the mechanism afterwards. But your product here is gonna be a beta keto ester, right? A beta keto ester. And what that looks like is gonna be like this right here. Let's actually do that so that I could make it more clear what's going on. Okay, so this is a beta keto ester because we have an ester right here. And let's focus on the carbonyl of the ester, like that. This is the alpha carbon, because that's the first carbon away from the carbonyl carbon. This is the beta carbon, because that's the second carbon away from the carbonyl carbon. At the beta carbon, we see a ketone. Right, so that's why we call this the beta keto ester, because there's a ketone beta to the ester. Okay. Any questions on that? Okay, before we move on to the mechanism, let me create a very quick synthesis problem for Kelly to try out really quick using these reactions here. Let's do that. And let's get to here. Boom. Like that. Okay, yeah, so try this out. It's gonna be 1, 2, 3 steps, right? Just gonna get that, and then that. First step, second step, box there, box here. Okay, try this one out for synthesis. Okay, so for the mechanism here, let me give you guys a clear example first, so then we could work with a clear example. Let's work with a simple ester first, which is this ester right here. And when I do claisen condensation, my reagents are going to be this. The first step is going to be an OR minus. But the OR minus here has to be the same OR as the ester, like that. If my OR is OCH2 CH3, my RO minus has to be like O minus CH2 CH3 as well, right?
And if it was different, it would be a different type of reaction. It wouldn't be a claisen condensation.
Yes, that's good. And you guys know the reaction already, and it's based on the chart that I showed you guys earlier, right? Like, let's say we use the same ester right here, but the first step I give you guys is this RO minus right here. What reaction would this be? There's a specific name of this reaction. Right, it's gonna be one of the carboxylic acid derivative reactions that you could use the chart for. Right, like when we have this ester here and we have RO minus, ester functional group, RO minus reagent.
Is it the transesterification?
Yes, transesterification, right? We're gonna convert that one ester that we started with a different ester. And the new OR group of the different ester, the new ester we're forming, is the OR group of the reagent we're using, right? So our product here, if you want to predict it quickly, is gonna be this right here, where the new OR group is coming from this reagent right there. Right, so that's trans esterification. Trans meaning different, esterification meaning we're creating an ester. Right.
Got it.
But if we use the same OR group right here with the ester, we're not going to do trans esterification because it's the same ester. We don't want to create the same ester. We're going to do something else. Think of this as a strong base. This strong base here is going to look for the most acidic acid. The most acidic acid here is going to be the alpha hydrogen. So this is the carbonyl carbon. This is the alpha carbon. And there's two alpha hydrogens here, right? This is an alpha hydrogen, and this is an alpha hydrogen. So what we're going to do is that we are going to deprotonate the alpha carbon by having this OR minus grab this hydrogen. The bond between this hydrogen and carbon being grabbed is going to create an enolate ion. Right, so it's going to create a double bond right here and push the double bond over to the oxygen right there. And now that's going to give us this intermediate right here. But once I have this enolate ion here, which atom is my nucleophile? Which atom is my nucleophile in this structure? This is going to be a little bit tricky question here. But this is based on quiz 4 material when you guys did aldol condensation, aldol dehydration. So this is a good final review as well. What's my nucleophilic atom?
Is it the alpha hydrogen on the new molecule you drew?
The alpha carbon.
Oh yeah, alpha carbon.
Yes. That's the nucleophile, not this negative charge on the O minus, even though there's a full negative charge there, right? It's this alpha carbon right here on the new molecule I drew. That's because when I draw you out the resonance structure, right, by moving this negative charge down to create the carbonyl, this double bond will go onto that carbon, giving that carbon a full negative charge. And this negative charge on the carbon right here is less stable than the negative charge on the oxygen, right? And because it's less stable, it's more reactive. So that's why the nucleophile, the more reactive thing, is this alpha carbon right there. Okay.
Is this the similar thing from the last quiz where there's one resonance structure that you can use both, but there's one that's easier to use to show the arrow pushing?
One that's easy to show the arrow pushing. You could use like yes. That is good. All right. Like when you have an electrophile nearby somewhere or an acid, right? And you react with this enolate ion here. The one that's easier is to start with this one here, right? Because you just directly attack the electrophile or hydrogen with the alpha carbon right there.
Yeah.
Right, you just directly attack it like that. If you use this resonance structure right here, you would have to draw two arrows. One to reform the carbonyl, and another one to attack the electrophile or acid.
Okay.
Right. But they're going to give the same exact product. They do the same exact thing, right? This one here is just a little bit more misleading.
Yeah, but we would still have to show that one, right? Because that's what we formed from attacking the alpha hydrogen.
Yes, and for Leeuwen's mechanism especially, she wants you to draw all resonance structures.
Yeah, okay.
Right, so she wants you to draw this, and there's one more here. What is the other resonance structure you can see from this structure here?
It could go down to the other side, the double bond? Or no? There would be a positive charge on that oxygen.
Yes. If this oxygen here went to create a double bond right there, that would push that double bond onto that carbon, giving us this resonance structure here, where we have a positive charge on this oxygen, and we get this oxygen there that's going to maintain negatively charged, and this is extremely unstable. This is a very, very minor resonance structure. right? Because there's so many formal charges there.
Yeah.
This is the major resonance structure. This exists more in nature, right? Because it's the most stable one. This is the minor one, but this one here is the one that clearly shows what's the nucleophile, which is this alpha carbon right here.
Okay.
Right. Okay. Now once we draw out all the resonance structures, we then bring in our electrophile, right? And you're gonna have two equivalents of this ester right here. We used our first equivalent already. Let's bring in our second equivalent of the ester, like that. What do you think is gonna happen between, let's use the easier one to draw out the mechanism with, this enolate ion and this second equivalent of the ester that we just brought in the mechanism? And don't worry, like if this shows up in the predicted product, I'll show you guys how to quickly predict the product as well, so you guys don't have to worry about drawing out all of these mechanism steps, right? But I want to go over the mechanism first because that's where the magic happens for this reaction, and then I'll show you guys how to predict the product quickly and what patterns to look for.
Does that attack at the carbonyl?
It attacks the carbonyl carbon. Yes, this alpha carbon here that's negatively charged is the nucleophile. This carbonyl carbon is the electrophile. So that is going to attack the carbonyl here, and there's one more arrow that happens after that attack. Because what happens when we attack the carbonyl here and create that new bond?
You have to push off one of the bonds to the oxygen.
Yes. Push off one of the bonds to the oxygen to create this tetrahedral intermediate. Now, this is a difficult one here. As a problem, like a challenge problem, try drawing an intermediate here. Try connecting those two pieces together. And let me see what you guys have. Trying to connect those two pieces together. This is like specifically why I like to use the star and dot technique to help me keep track of every single group. Right. Madison, Jenna, Maggie. Whenever you guys have it, you guys can send it to me on the Zoom or text me. On Layla, Peyton, for 118B, what would you guys like to go over today? Probably aldol condensation, huh? Aldol condensation micro edition for 118B. The new material chapter 18 stuff. Or imine, enamine. Yes, the three reactions that were the hardest for chapter 18. So I think that is aldol condensation, which is good review for 8B. Dehydration. This is also good review. Micro edition. Wait, I don't know if 8B went over this. I forgot. Micro edition. 1.4 edition. Conjugate edition. Yeah, 8B definitely went over this. 1.4 edition. Conjugate edition. Right. And then that would lead to do Robinson annihilation with an intramolecular aldol condensation reaction. Right? First step, micro. Second step, intramolecular aldol condensation. Those two steps together is the big reaction Robinson annihilation. Okay, and then the other thing that I want you guys to know is, oh yeah, direct addition, aka 1-2 addition versus conjugate addition. So this is the easier one. The shorter one, I would say. 1-4 addition. Okay. These three we will try to get through today. Okay. Does anyone have this connected piece together for this result?
I sent it.
Let me see. Okay, got it. Attack, push that up there. New bond, star dot has 1, 2, 3, 4. O minus star. Oh, okay, guys, I see. Your dot is on top, your star is on bottom. Okay, and OR star stage 2, stage 3. Yes, that is correct. That is the correct structure right there.
Yay.
Yes, you got it. Right. So what I'm gonna do here is draw out the starred molecule on top like this, which this is the starred molecule right here. This is the new bond between the star and dot molecule. New bond. This dot molecule here is attached to a propyl group, 1, 2, 3, an OR group, OR, and it was double bonded to an oxygen, but it's now single bonded to an O minus, like that. Okay. Now, once we have this right here, we're going to reform. Okay, there's two directions that we could go here, right? We're either gonna protonate the O minus, or we could kick out a leaving group. Which direction do you guys think we can go to? Right, like
No.
You want
like,
to
is there
reform the O minus, so then you
like
because you want to. Don't you want to keep that, right?
Yes, we want to keep this group, right?
And then kick out the leaving group.
Kick out the leaving group. This is the leaving group right here, the OR right there. That can leave because we're in basic conditions, right? We're not gonna protonate it yet. Like, we're not gonna bring in the acid just yet. We're gonna reform the carbonyl, carbon double bond oxygen, and kick out that OR group right there, right? And this right here is a bad leaving group, right? So it's gonna leave, but it's able to leave because we're in basic conditions here. But when it leaves, it's very angry, right? It's very, very angry. So it's gonna come back for, this is a very important step in the mechanism here. It's gonna come back for vengeance, right? And to do that, it's gonna deprotonate the alpha hydrogen in between the two carbonyls, right? Because this is also an alpha carbon because it's one carbon away from the carbonyl carbon, but we're not gonna deprotonate the alpha hydrogen because it's not acidic as this alpha hydrogen right here. It is acidic, but not as acidic as this alpha hydrogen in between the two carbonyls. It's alpha to both carbonyls. So we're gonna grab the one in between the two carbonyls, grab the hydrogen in between the two carbonyls, and give the alpha carbon a negative charge, right? And this right here is like the irreversible step. But I see on her lecture notes that she says it could go backwards a little bit, but it's gonna favorably, like majority, go forward in this direction here, because once that bad angry leaving group gets protonated, it's now happy and stable, and it doesn't want to go back to its unstable state, right? So it wants to stay in this stable state, so it's not gonna go back as much. So this is the irreversible reaction step in this mechanism. Okay, now this is the end of the first step. The second step is when we bring in the acid workup, H3O+.
I have a quick question before you do that.
Yeah.
So, because I did the dot up and the star down, I'm kind of confused how to like draw it after I push the negative charge down. It's just like a double bond at the end of the molecule.
Yes, so the way that you drew it, right? When you push the double bond down to kick out the OR group, you have to like that very long single bond that you drew out connecting the star and dot, you have to like rotate it to the right, bring it up. Yes, bring it up.
Okay. And then okay, I see it now.
Yeah. Right. Okay. And this leads us to our last answer, final product. Right, which is an acid-base reaction. Let me see. which is going to be that right there. And this is a beta keto ester, like we talked about earlier, because this is the carbonyl-carbon of the ester. This is the alpha carbon. This is the beta carbon. At the beta carbon, there's a ketone. So this is a beta keto ester. Okay. Nice.
Wait. I got stuck again. Can I show you what like I redrew it, but I couldn't figure out how to do the acid workup.
Yes. And then after this, I'll go over the shortcut on how to predict the product quickly for this claisen condensation stuff, and then I'll move on to 118B aldol condensation, because this is a good segue for that. Like, this mechanism here is very similar to aldol condensation for 118B and aldol dehydration.
Oh, I sent it.
I see. Okay, you reform carbonyl, kick out that OR group, and then you got that carbonyl there. That is attached to this starred ethyl. Yeah, that's good. You drew it correctly.
But then the acid workup, could you explain that part again?
Yes. The acid workup, right? You know how you kick out the OR minus, right? This is a very angry OR minus. Very angry guy right now.
Oh, okay.
Right? So it's gonna look for vengeance. It's gonna look for the most acidic proton, which is this one right here, in between the two carbonyls.
Yeah.
Right? So, like, you basically already have your final answer here, right? Because that final answer there is this final answer right here. So if this was predicted product, then if you draw that, that's full credit. But if this is a mechanism problem, she might want you to draw this vengeance step, where the angry OR minus grabs that alpha hydrogen between the two carbonyls to give the negative charge on the alpha carbon, and then you bring in the acid workup to get back to the what we started with, right?
Yeah.
But that point of that step is just to quench this angry leaving group, to satisfy that angry leaving group, to make it happy and stable.
Okay, and then that leaves behind a negative charge, and that's when we do the acid workup to give back.
And this comes from the second step.
Okay.
Yes. Right. And the way that you drew it, Jenna, is the exact same structure as this. It's just rotated somehow in the bonds.
Yeah.
Right. And the way that you drew it is the more clean way to draw it, more aesthetic way. Like that. Right. But this is how like yeah, don't worry about drawing it like this. If you draw it like this, you get full credit. I wanted to draw it in this way so then I don't like overwhelm you guys on drawing it the clean way. But you could just do it like this. But that's good. That's good. Okay. Let me show you guys how to predict the product quickly here. And then I'll move on to 118B aldol condensation, aldol dehydration. So when you have an ester and you have two equivalents of it, and you react it with an OR minus, where the OR minus matches with the OR of the ester. To predict the product quickly, find your star and dot. We know our star is the alpha carbon. We know our dot is the carbonyl carbon. So what we're gonna do is that we're going to connect the star and dot right away. That's a star. This is the dot. Right? And at the starred molecule, you guys remember how back in the aldol condensation days, feels like a long time ago, but it was just like a couple weeks ago probably. The starred molecule stays the exact same. Nothing touches that starred molecule, right? Everything stays the same.
Yeah.
The dot molecule is the one that changes. So the dot molecule here has the carbonyl and the R group. 1, 2, 3. The starred carbon here is part of the molecule. So the dot. So that's 1, 2, 3 carbons. 1, 2, 3 carbons. Just completely get rid of the OR of the dot, and that's your final answer. Right? Because this OR here is the leaving group. When you think about the mechanism, that left in the mechanism.
Oh, okay.
Yeah.
So you copy and pasted the starting material, and then you took another one and you attached it from the star,
Mm-hmm.
but then you can like copy and paste it and then just erase the OR group.
Yes, like copy and paste that whole structure with the dot, and erase the whole OR group, right? But be careful here. Like this dot here, the R group, this is included in it, right?
Yeah.
That's this thing right here is this thing right here, right?
Okay.
Yes.
So if there was no acid workup, would that carbonyl just be an O minus?
Yes. If there was no acid workup, this alpha carbon here would be O minus.
Oh, the alpha.
This alpha carbon here, yes.
Okay.
Or you could draw it like this. Right. Or like this. One of its resonance structures, right? Because this alpha carbon here, if it has a negative charge, it could do resonance with both carbonyls, giving us these other resonance structures here.
That's if there's no acid workup.
Yeah, that's if there's no acid workup. If there's no acid workup, you're gonna get these structures here. They're the same thing, but resonance structures of each other.
Okay.
Right. This one here is probably the major one. It's the major one. Right.
Yeah.
It's major compared to this one because this one here is competing for resonance with this OR group right there. There's competition of resonance, making it less stable.
Yeah.
Yeah. But don't worry about that. But just in case it shows up, you know.
Oh, okay. So it's not really common to see no acid workup.
Yes, it's not really common to see no acid workup. I haven't seen Lieben's test no acid workup for this reaction. Right?
Okay.
She only tests no acid workup for like the deprotonating carboxylic acid reactions, like this chart right here. These are the common ones that you need to know if there's no acid workup to create the carboxylate negative charge for Lieben's. Right.
Okay.
Okay. Now I'm gonna give you guys a practice claisen condensation problem, and you guys can predict the product. Right? Use the shortcut and the mechanism just to practice both skills. To save time on the mechanism on the quiz. Let's do this. Okay. And we're gonna react it with, like, this is gonna be two equivalents. We're gonna react it with that and acid workup. Predict the product and draw out the full mechanism. Include resonance structures where possible for full points. Okay. Now, I'm gonna do 118B aldol condensation, aldol dehydration reaction, which is very similar to what we just did here. So, aldol condensation.
Wait, Bryant, sorry, could you go back 1 second? I forgot to take a photo.
Yeah.
Okay, thank you. I got it.
Yes. Okay. Aldol condensation. The general reaction here is gonna have an aldehyde or a ketone, usually an aldehyde. I'll tell you when to use a ketone, but usually an aldehyde. Aldehyde or ketone reacting with a first step strong base. Right? Do you need acid workup for this step? For this reaction? Let's see. Attack, go back down. Yes, you need acid workup for this as well. Second step, acid workup, which is usually H3O plus. You can see HCl or H2SO4 as well, but usually H3O plus acid workup. And a strong base here, it could be OH minus, it could be OR minus. Right, those are the common ones that you see. And the R is like variable. It could be OCH3 minus, it could be OCH2CH3 minus. That's gonna give you, if this is aldol condensation, it's just gonna give you an aldol, right? Which is eventually gonna become something called an alpha, beta, unsaturated carbonyl. And I'll go over what these means when I go over the mechanism, but these are just the terms that are gonna be the big picture. So when you guys go back to this review, you guys can understand what these means more clearly. Right? And this is gonna be with heat. Right? But if you have heat, then that's gonna go to aldol dehydration. Right? Heat, aldol dehydration, which would create the alpha beta unsaturated carbonyl. The short name of that is an enone. Okay, let's get started. There's 3 types of aldol reactions though. There's a self-aldol, there's a mixed or crossed aldol, and then there's an intramolecular aldol. Let's start with the easy one, self-aldol. I'll show you the mechanism, how to predict the product quickly, and then give you guys practice after. Okay, so let's start off with a simple aldehyde. Let's start off with this aldehyde right here. And let's do a common base, ethoxide, Helix's favorite base. And then second step, acid workup, H3O+. So this strong base here is going to look for the most acidic acid, right? That's the alpha hydrogen. We're going to grab that hydrogen, and you could either do 2 things here. You could either give the alpha carbon a negative charge, or you could generate the enolate ion. You could create a double bond here and push the double bond into the oxygen right there. That's what Helix probably does, so we'll do that. Right? This right here is an enolate ion. Right? This is an enolate ion. And the reason why professors draw it in this form here is because this is the major resonance structure. But it's very misleading because even though there's a negative charge on oxygen right there, that's not our nucleophile. Right? Our nucleophile is this alpha carbon right here, which I'm going to star out. The reason why is because if I draw you out the resonance structure like that, we're going to have a negative charge on that alpha carbon, which is less stable than the negative charge on the oxygen. Right? And because it's less stable, it's more reactive. So that's why this is my starred atom here, my nucleophilic atom there. Right? That's why I told you guys earlier that when you grab this hydrogen here, you could give the negative charge on that carbon instead, leading directly to this right here. Right? Now, assume for Helix's class that this aldehyde is in excess. Even though he doesn't say 2 equivalents are excess, assume that that starting material, the aldehyde, is in excess. So we're going to bring in a second equivalent of the aldehyde here, where my electrophile is this carbonyl carbon right there, right? Because it's positively charged. That's my dot carbon, the electrophile carbon. Now, you could either use this form or this form to attack that carbon right there. If you want to use this form here, the simple form, you could just directly attack the carbonyl carbon, pop the double bond into the oxygen. If you want to use this form right here, you gotta reform the carbonyl and have the star carbon attack the carbonyl carbon and pop the double bond into the oxygen like that. Now, this is the tricky part here, trying to connect these 2 pieces together. This is why I've been starring and dotting my nucleophiles and electrophiles, right? This is my starred carbon here. This is going to be the new bond between the starred and dot carbon right here. Now I draw whatever is attached to my dot carbon. I already drew out everything attached to my starred carbon, right? The starred carbon has this methyl group and this aldehyde. This is the new bond from this attack, connecting the star and dot bond together. Star and dot carbon together. Now I draw what's attached to my dot carbon. This dot carbon here is attached to an ethyl group, a hydrogen, but I'm going to leave that as invisible. You don't have to draw that out. You can if you want to, but you don't have to. It's invisible now. It was double bonded to an oxygen, but we popped that double bond to the oxygen to create a single bond O-. Right? Now, once we have this single bond O- right there, we then bring in let's say the neutral solvent to protonate the O-. We're not going to bring in acid workup just yet. to create this neutral OH right here. Right. And I just realized that we actually do not need acid workup here. So I'm gonna have to look at helix's selection also again to see if this reaction needs acid workup, but probably not. Like you're just probably gonna see the strong base here with the solvent for this reaction to go through, right? So we do not use acid workup here. This right here is our aldol, which is an aldehyde and then alcohol. Ald for aldehyde, all for alcohol. And they're beta to each other because this is the carbonyl carbon, this is the alpha carbon, the first carbon away, this is the beta carbon. Right. Now we usually would not stop here, right? Sometimes Helix does though, because I've seen some of his exams where he stops here. And before we get to that point though, I want to go over the regular one first. So now assume that we have heat, which we will usually have, right? This alpha hydrogen right here in between the carbonyl and alcohol is going to get deprotonated. That's the most acidic hydrogen, right? So another base, OR minus, is going to grab that hydrogen and form another enolate ion, right? Generate another enolate ion. Right, now once we have that, we're gonna do a boomerang. We're gonna go back around, form a carbonyl right there, make a double bond right here, and then kick out the leaving group OH right there. Right, this OH here is able to leave as a leaving group because we are in basic conditions, and that's gonna give us our final answer here. This alpha beta unsaturated carbonyl, like that, right? This is the carbonyl carbon. This is the alpha carbon. This is the beta carbon. And we see that in between the alpha and beta carbon, there's a double bond right there, an unsaturation between them. Right? A double bond is an unsaturation. So this is an alpha, beta, unsaturated carbonyl. Okay. So that's aldol dehydration right there. Aldol condensation right there. The first step of the mechanism, deprotonate the alpha hydrogen to create the enolate ion. Once we get the enolate ion, we bring in a second equivalent of the aldehyde to attack to create this intermediate right here. This is the tricky part, connecting those two pieces together with the star and dot, right? And then from there, we protonate the O minus with the neutral alcohol to create this neutral product. Then we bring in another base to deprotonate the alpha hydrogen between the carbonyl and alcohol to create this enolate ion. Then once with the enolate ion, we reform the carbonyl, we push the double bond over and kick out the leaving group to create this final product, alpha beta unsaturated carbonyl. Any questions on this mechanism before I show you guys the shortcut on how to predict the product quickly? Layla Payton?
Was there any reason we had to draw like the two resonance structures, or is that kind of just more conceptual?
That's more conceptual. You did not have to draw out the two resonance structures for Helix's mechanism problem. You don't have to draw those out, right? You could just stick with one, and you get full credit for it. The name of this mechanism is aldol condensation, or aldol dehydration. And for you, since you're in 8B, this is quiz 4 material. So this is good final reveal. It won't be on this week's quiz, this Friday's quiz. This is aldol condensation, but it's very similar to claisen condensation. Okay. Now, if there's no other questions, let me show you guys how to predict the product quickly here. Let's use that same aldehyde, right, to check our answers after if I'm going to predict this correctly or not. The reagents here, no acid workup, right? Just a base and its solvent. First thing we do, like we just did in the claisen condensation previously, find the star and dot. The starred carbon is the alpha carbon, this carbon right here, the first carbon away from the carbonyl carbon. Then you find the dot carbon, the carbonyl carbon right there. To predict the product quickly for aldol dehydration, draw out the starred molecule like that. This is the starred carbon right here, right? And the starred carbon has a methyl group and the aldehyde like that, right? That's good. Now we draw the new bond between the star and dot carbon. Right, that's the new bond right there. Now, if this can go all the way through, which usually is the case, it can go all the way through. Tomorrow, office hours, if we have time, which we probably will, I'll go over the cases where you cannot go all the way through. And that's important for Helix because that's rare though. I've only seen him test it once or like twice where he doesn't go all the way through with this reaction. The dot carbon here, right? Draw what's attached to it. It's attached to the hydrogen, but it's going to be invisible. We don't have to draw that out. You can if you want to, but it's invisible. It's attached to this ethyl group, CH2, CH3. So I'm going to draw that ethyl group like this. CH2, CH3. The carbonyl, completely get rid of that. Completely get rid of the carbon double oxygen. Ignore that, right? And then you put a double bond between the star and dot carbon, like that. And that is going to be your final answer, which is this right here. And that's how you can predict the product quickly for aldol condensation. Any questions on that before I give you guys practice to predict the product here and the mechanism, draw out the mechanism for this one, for 118B? Okay, for practice, just predict the product here using the shortcut I just showed you. You could practice the mechanism after, but take a screenshot of this, practice the shortcut I just showed you to predict the aldol dehydration product here for this aldol dehydration product reaction. Okay, now I'm gonna check your guys' work for 8B here. Have you guys got this? I got Maggie, so let me check hers. But Jenna, Madison?
Yeah, I'll send it.
Yes. Let me rotate. Okay. Practice claisen. So you did the mechanism and predict the product. Deprotonate, generate enolate ion, draw out all the resonance structures. And I don't know if this is a big deal for leave-ins. When you draw out resonance structures, make sure to draw out the double-headed arrow like that. Between the resonance structures, right? It might be a big deal for leave-ins, I don't know. But that's good. You drew out all the resonance structures, and then have the alpha carbon attack the carbonyl carbon, push the double bond to oxygen, create that tetrahedral intermediate, and then connect those two pieces together. Star dot is attached to O minus. That OR right there, Maggie, is not a tert-butyl group, right? It's a isopropyl group. So keep that in mind as well. Because I think she will like take points off for like adding an extra carbon or losing a carbon by accident. But you get the overall big idea, so that's good. And then we have that R group right there, reform carbonyl, kick that out. It's angry, right? But it's not a tert-butoxide. It's gonna be isopropoxide, right? Because it's gonna be isopropyl group. It's gonna go back towards vengeance. Deprotonate the alpha hydrogen in between the two carbonyls, and then that alpha carbon gets protonated by the acid workup to get the final answer, which is a beta keto ester. Right at the beta carbon, you have a ketone to the ester, and that ester there, be careful. The R group is an isopropyl group, not a tert-butyl group. Right, so keep that in mind. Let me see the star and dot technique to see if this is the right answer. Star dot. Get rid of that OR group completely. Yes, that's the right answer. You got it, Maggie. But just keep in mind that it is not this, right? It is gonna be this, like that. Okay, nice. Let me check. Yeah, I know. I think you guys are used to seeing a lot of tert-butyls. That's why you put that tert-butyl down like that. But that's why it can be tricky. I got Madison's. Let me check Madison's here, right? We're going to let's see, star dot CH2 boom. Yep, you got the right product, Madison, using that technique. Let me check your mechanism.
I just started like a couple things for it. I got a little bit stuck on like that third step, I guess you could say.
Right, when you have the alpha carbon, the negative charge, right?
Yes.
Right there. This is when you bring in the second equivalent of the thing of the ester, and then you attack the carbonyl carbon, pop that up there, and that's when you connect those two pieces together like that. Right, and
okay.
and then you get this weird tetrahedral intermediate. Where is it? Right here. Like you get this bulky group right there, and then from there you kick out the leaving group, which is angry, and then it goes back for vengeance, and then you quench it. Okay, yeah. So practice with that. But you got the right answer for predicted product, so that's good.
Okay.
Did you use that technique I showed you on the shortcut?
Yes.
That's good. That's good.
Yes.
That's good. Okay, let me check Jenna's. For this one, the product star dot. Oh, Jenna, so your dot, right? Your dot is not the alpha carbon, because when you do that trick, right? We're going to, so let's do this. This is our star right here. This is our dot right there.
Wait, I did that though.
Yes, you did that. But when you're gonna connect your star and dot,
Oh.
right?
Oh, you connected at the dot.
Yes, this star here is gonna connect it to the dot. And what was our dot again?
The carbonyl carbon.
Yes, and that's gonna be a carbonyl carbon right there.
Oh.
And what is the dot attached to in the final product?
It's attached. Oh, we have to get rid of the OR group.
Yes,
So
the OR group is no longer there in the final product.
oh, right.
Okay. But it's attached to this R group right here, which is a CH2 ring, like that.
Oh.
Yes. What you did, right? You connected the two alpha carbons together. Right? But we will only want to connect the alpha carbon to the carbonyl carbon. That's the new bond right there.
Wait, so I connected it correctly at the star. Like I formed the bond at the star. I just I have to add a carbonyl carbon directly to that bond.
Yes. Right. A carbonyl carbon to that bond. You connected the star carbon to another alpha carbon.
Okay.
But we want to connect the star carbon to the carbonyl carbon, not the alpha carbon.
Yeah.
Yes.
Is it something wrong in my mechanism?
So your mechanism, deprotonate, generate the enolate ion, draw out the resonance structures, alpha carbon attacks the carbonyl carbon, push that up there. So you had the right arrows, right? What alpha carbon attacks the carbonyl carbon, popped the bond onto the oxygen, but you drew out the connection incorrectly. The one that I said was the trickiest part of the mechanism. Right?
Oh my god. I literally, I did the arrow to the dot, but I added the bond to the star.
Yeah, that was where you went wrong right there.
Oh, okay. I see it now.
Yeah, and then once you get that tetrahedral intermediate, that's when we kick out the OR group, and then it goes back for vengeance, and then we protonate it at the end. Yeah.
Oh, okay.
That's good. Yeah. Okay. Now, Layla, Peyton, did you guys get this aldol condensation product, predicted product shortcut I showed you guys? Yeah, let me explain the aldol condensation shortcut one more time.
Thank you. By the way.
Yeah, guys. So this is gonna be the star carbon, which is the alpha carbon. The dot carbon is the carbonyl carbon. To predict the product, right? Draw out the starred carbon molecule first. This is the starred carbon molecule. Everything else stays the same, right? The exact carbon copy of that. Make a new bond to the star and dot carbon, right? This is the new bond right here, new. This dot carbon here is gonna have everything besides the carbonyl carbon. We completely get rid of that for aldol dehydration, right? The dot carbon here still has the hydrogen, and it still has the ethyl group right there. We just put a double bond between the star and dot carbon to get the final answer, right? The double bond between the star and dot carbon. Does that make sense, Peyton? Yes. Okay. Let me check Layla's answer for this. Okay. Star, dot, and the dot is attached to a CH2 ring, and this is an alpha beta unsaturated carbonyl. That is correct. You got it. Nice. You got it, Layla. I would just practice the mechanism because this is a high yield mechanism problem for the final for Helix. right? This is the starred molecule, the alpha carbon. This is the dot carbon, the carbonyl carbon. And I am going to draw out the starred molecule as it is, carbon copy, which is this structure here. Done. Next step. Make a new bond between a star carbon and dot carbon. Done. Next step. The dot carbon no longer has the carbonyl. It's still attached to the hydrogen, but we can leave that as invisible. Don't have to draw that out. And it's attached to a CH2 benzene ring. CH2 benzene ring. Right? A common mistake is that students draw out this ring and they draw the benzene ring from here. That's too early. Right? Because this carbon here is that carbon right there. That starred carbon right there. And that starred carbon is not a benzene ring. It's not part of the benzene ring. It's a CH2. Okay, now from here, the final step to get the final answer is put a double bond between the star and dot, giving you your final answer, which is an alpha, beta, unsaturated carbonyl. Right, because we see an unsaturation between the alpha and beta carbon. Any questions on that? On the shortcut that I just did right there for this aldol dehydration predicted product problem? I would practice the mechanism here. Just for practice, you know. Okay, let's get.
I have a quick question.
Mm-hmm.
So I was attaching both of them, and is it that, wait, let me just show you.
Mm-hmm. For this one specifically, the aldol dehydration one?
Oh no, for the claisen.
Claisen, okay, this one.
Yeah. Okay, I sent it. So is there, do I just directly form the carbon on the dot, or is there that O- first?
For the mechanism?
Yeah.
That is correct now. The alpha carbon attacks the dot carbon, which is the carbonyl carbon, and that carbonyl carbon is no longer attached to a double bond oxygen. It's now single bond to O-. The R group is there, but you're missing one thing to the dot carbon. There's one more thing attached to the dot carbon.
Is it the OR group?
The OR group, yes.
Okay, and then after that, I show the arrow going down and kicking out that group?
Yes. And then that group would be very angry.
Oh, and then that's when I do the acid workup.
Right after you deprocynate the alpha carbon in between the two carbonyls, and then you do the acid workup to get to the final answer. Yes.
Okay.
Yes. Yeah, so it is a lot for sure for the first time you guys are seeing this, like both 8B and 118B, aldol dehydration, aldol condensation, claisen condensation, right? But I gave you guys a shortcut on how to predict the product quickly. Practice that, right? Until you could like have a procedure like memorized in your head or write it down in your note card with that procedure for the shortcut. And practice the mechanism as well, because that's where the magic happens. Like if you understand the mechanism behind these reactions, and explain and walk yourself through it like a story and why things do like they do, like this angry leaving group here is gonna go back for vengeance. It's gonna stick with you even more, and you could like understand the reaction even more, and you could like remember it more during the exam. You know.
Thank you.
Yeah.
Okay. Yeah. Is malonic ester synthesis harder?
No.
Okay.
I would say claisen is harder than malonic and acetoester synthesis. The tricky part about those ones are decarboxylation. The mechanism for decarboxylation could be tricky.
Okay.
Decarboxylation, but it's shorter than this one for sure.
Okay, I'll go over that.
Yes.
Thank you.
Have
a good night.
Have a good night, guys.
Bye.
Bye.
Thank you. Good night.
Good night, Layla. Good night, Maggie. See ya. Oh my goodness, long office hours.
That was so long.
I know. Time flew. Like I was just yapping, talking.
Oh yeah, you were on a roll.
Yes, I was. Hold on.